Welcome to another CO2 Design Fundamental Training. Yesterday, if you weren't here at the session, for sure, this one here is going to help us because we talked about some quick design yesterday. Today, we're going to be diving into avoiding costly mistakes because we've seen this time and time again. And Chris seen this tons of times on making one small adjustment can cost a lot of energy or cause a lot of issues. We've talked about a few of them yesterday, but we're going to be diving into it deep today. Chris, how you doing, brother?
Very well, Trevor. Thanks for having me back. Looking forward to this one as well. It's a bit more of a storytelling one as much as anything today. Thankfully, none of my personal designs have suffered these issues, but it's not that easy to avoid sometimes. So having these things in mind is always useful to have. So hopefully it's going to be a beneficial session for those who are able to watch.
Awesome. I'm excited.
All right. Should we dive straight in?
I think so, because these are just some of the things that is so important and key to a design. And when you're learning and developing CO2 design, you want to see what you don't want to do for sure. You want to learn how to do it, but you want to learn what not to do as well.
Definitely. So today we want to avoid any costly CO2 piping mistakes. And I mean, costly can range from, the actual cost of maybe you've got piping which is too big. Maybe you've spent more money than you need to. Maybe you've sized it too small. You have an excessive suction pressure drop, and now your compressors are running more, a worse condition. Maybe it's time spent in having to retrofit and upgrade pipe sizes or remove pipework sections that were installed incorrectly. All these things cost time and cost money. So let's have a look at what we tend to get. So I find it's generally five things which what we can class as, a mistake. So if we size our pipework too small, we're not going to get enough mass flow through the system. So we're going to have insufficient cooling capacity. We can also get that if oil migrates to an evaporator where it's going to want to go, tries to get to the coldest spot. If there's no oil management system installed, and we have to encourage it back. If our pipework isn't designed correctly, that oil will not return. With excessive pressure drop, we'll get a loss in efficiency. Our compressors will run at a lower SST, lower saturated condition, and have to do more work to lift it to our condensing and our discharge temperature. We'll have excessive installation costs if we size too large, or if we take a route which isn't planned very well, not liaising with other services. So, for example, sprinklers, ductwork, etc. Try and have a sensible route through a store rather than having to weave around everything, introducing more bends, more pressure drop. Regarding materials, particularly with CO2, this is even more of a risk than it's ever been before, but overpressure as well. Making sure our pipework is actually fit for purpose and can accommodate the pressures we're working with. For those who aren't too familiar with CO2, but are familiar with other refrigerants, for example, 404A, you tend to have for a chiller system a suction pressure of about 3 bar, it's about 45, 50 psi, and a discharge pressure of about 20 bar at most. Well, our suction pressure on a CO2 system will be 28 bar. So it's higher than generally the highest discharge pressure you would get on 404A. You're getting up there for the discharge pressures on air conditioning systems, 410 or R32. So we need to accommodate that in our pipework selection. And then if we undersize our pipework, or if we have too many short radius bends, we can get noise and vibration occurring from pipework, particularly on liquid lines. If a liquid line is sized too small and our velocity is too high, when any valve decides to shut fully, you'll get all that energy having to find its way somewhere to go. It's not just going to stop moving without dispersing that energy. That will go into the walls of the pipe, into the valve body. It will potentially corrode the inside walls of the pipe. It will damage that valve over time, and it's unwanted. It will be costly to replace. So with all these issues, the main ones we want to look at are what happens to inadequate oil return design, incorrect material selection, and poor layout and routing through a store.
And that's, I think, incorrect material selection is something that I've seen multiple times in different ones, training courses from our design to my other CO2 courses, because like K65 or XHP, whatever it is, that high pressure copper, a lot of technicians don't know about it, and it looks the same. It's the same length. It looks, it is heavier. If you look at it closely, you can tell one has a bigger diameter than the other. The big thing is that, man, when I worked on lots of construction jobs, we would just grab pipes and pull them in and just go start putting them in. But I've heard of stores where they put all K copper on the high side, and that is something you cannot do. And as a designer, you need to make sure when you're designing, drawing this out, that you label it correctly after you do the design, so that they understand what you need to put in there. Because here in Canada, you have to use stainless steel. Yeah, you're not using any high pressure copper on the discharge lines.
Definitely. Again, where you are in the world will depend on that. Because in the UK, we can use K65 on the high side, but it has to be rated at 120 bar pressure. Whereas normally we'd also get 80 bar pressure pipe, which we'll happily do the sales for. But even then, we're now getting systems which operate at 90 bar out of the intermediate side through to a liquid. So we're now having to install extra high pressure K65 pipework rated to 120 bar to accommodate those liquid lines. And it just keeps going up and up and up. And also, depending where you are in the world, you may have to use stainless steel as mandated by local codes rather than it just being good engineering practice. So first off, we're going to dive into inadequate oil return design. So main thing in piping design is we want it to slope downhill on our suction line to encourage oil to return with gravity. If we don't, we have to try and force it alongside entrained in refrigerant, particularly when we work against gravity. So we're looking at suction risers. So if we don't, effectively all the oil that's in our system, we don't have a correctly installed and maintained oil management system, we need to encourage that oil to return at all times. With a correct oil management system, we should be able to rely mostly on it staying around the compressors at least, and then just encouraging any small amounts of oil that flow out of the system to return. With a condensing unit, with CO2 condensing units nowadays with rotary compressors, they don't hold a lot of oil inside them, if any. So you'll find that oil migrates out of the condensing unit, away from the compressor, and finds its way to the evaporator. So they'll have control systems normally in place now that every so often the condensing unit will talk to the evaporator's expansion valve controller. It will tell that valve to open completely full, allow all the liquid to flow through and carry that oil, displace it, and take it back to the condensing unit. With multi-compressor systems on racks, we want to just encourage it to return using suction risers as shown. So I've got an example here on the right-hand side of what I class good practice and poor practice. So our good practice on the left-hand side, unfortunately has a cage in front of it, but I thought that's a very nicely installed trap, is we have a proper oil trap installed on this riser. It falls below the lowest point of the pipe feeding into it. So at times of part load, that will fill until pressure behind builds and force it back up. On the right-hand side, we're going against gravity, but it does not have a trap at the bottom. Oil will find its way back into the evaporators instead when it reaches periods of low load, and then it has to try and force its way back out of the evaporators and then up that riser as well. It just leads to more likelihood of oil logging in those evaporators, reducing the cooling performance of the coil because it's now got an insulative fluid inside it as well, and reduce system capacity. That's if we don't encounter compressor issues before that, because we've not got enough oil in them to lubricate the compressors. CO2 is a bit more forgiving than HFC in this sense. It's much denser at the conditions we use, and it's a very good refrigerant for returning oil in training it and working against gravity. Generally, this means when we're doing our pipe sizes, but we can get away with lower velocities. We don't actually have as much energy through velocity of the fluid to carry the oil back to where it needs to go. But we still need to consider it. So we still have our rules of thumb for design velocities, as we touched on them slightly yesterday. but making sure that's actually implemented on site is very important. I've known of sites where the designers have designed it correctly, and they've shown risers maybe 1 or 2 pipe sizes down, as you typically would, and the installation engineers on site just being, well, we've not got that pipe, let's just use that pipe instead. But we haven't got to get reducers as well. Well, you're risking a lot there. It might be sized perfectly well to accommodate a full load, but when we get down to part load conditions, there's not going to be any velocity behind that to try and return that oil. So making sure it's actually designed effectively is important there.
I totally agree with that. And I think this comes back to any refrigeration design practices. Getting in there, talking with them how to pipe it properly, because sometimes people installing are new to it, and it's so important to have those traps there. I really I've seen it on old renos that I used to do, where sometimes they did not have any insulation, they did not have traps. They're like, oh, well, it's only 3.5 feet or a meter. You don't really need a trap for that because it's not high enough. But I've seen when I cut out coils before, they were just full, like the whole bottom of a evaporator full of oil. Lots of times.
Completely oil logged. Just what you want to do when you're ripping them apart is get covered in 2 liters of oil.
Yeah.
So onto basically how can we actually encourage oil to return or not log in our evaporators? So we have our best practices here. Our minimum velocities for our horizontal sections of suction, generally between 4.5 to 8 meters a second velocity, 900 to 1600 feet per minute. And on vertical rises, between 8 and 12 meters a second, or 1600 to 2400 feet per minute. Those who are familiar with rules of thumb for pipe sizing will know, so those are lower than HFC refrigerants. We will also make sure on horizontal sections that we have a proper pipe slope implemented. Some people believe or specify as long as it's greater than 0.5% or 1 in 200 fall, that should be okay. I'd rather it go to at least a 1% fall or 1 in 100. So over 100 inches, it drops down by 1 inch. Avoiding oversized pipe work. Oversizing it reduces velocity, leading to oil pooling, and as is avoiding costly errors. Oversizing, you're going to have more expensive pipe work. A larger pipe as well will generally need to be a thicker gauge pipe work as well, because as it expands, you have more pressure forcing out the walls. And anyone who's looked at a pressure table for pipe work will notice as the pipe gets bigger, the maximum working pressure at the same gauge is lower. So you also need to consider that, making sure the pipe work is suitable for that scenario, even if it is oversized. And then, more importantly, at the design stage and when you're selecting equipment, or designing equipment, if you're in the manufacturing world, is including oil separators. Having actual oil separators sized for the full load of your compressors, peak load conditions, with that oil flow from either a reciprocating compressor or scroll compressor, making sure it can remove as much of that oil as possible from the discharge gas before it exits that area off to your gas cooler. At part load, you might find that these oil separators aren't as efficient at doing their job now, and actually you'll find that oil escapes more at part load conditions than full load conditions. Well, what can we do about that? We could install multiple separators in parallel. We could have one separator per compressor, or feeding into one or multiple oil reservoirs as well. So looking at these conditions at full load and part load is very important, because part load condition is where oil management is more important, in my opinion.
Yeah, and I think in piping design, I know in module 10 of the 12-week course, when we dive into oil management, sizing those oil lines is so vital as well. So we're talking more on the refrigerant side as this time, but on those oil lines, if you undersize those, you're going to run into a world of issues. And I've seen it multiple times in conversation in courses where they're like, we're just not getting oil on the oil transfer solenoid, the way it opens up. Because when you're designing the oil management, there's 5 or 6 different designs you can do, which is we talk about in the program. And so you want to understand when that oil transfer solenoid opens up, if that's the design you use, that needs to make sure you're moving enough oil into those compressors. And then those compressors have a certain amount of carryover. You got to understand all that stuff in the piping design of the oil management system, which is a whole different game than designing the piping of the refrigeration system. So it's important, really, really important to dive into that stuff when you're doing those sizing, because I know we included the oil separator there in the sizing. It's so many times that you need to sit down and you got to make sure that that's correct, those lines.
Definitely. And 99% of the time, you can rely on it and be, well, it's been designed correctly. Designers of equipment are doing their due diligence, but they can't design that equipment to suit every single scenario that's out there. So if you do find an odd site and you're scratching your head thinking, why isn't this working? At least if you know how to size an oil separator system, you can do your checks to see, is this the correct system for that application, for that site? So again, the large industrial equipment, you might need multiple separators in parallel. Sometimes you might get away with one, or you may need to have several just to accommodate full mass flow at full load conditions. If we're talking, half a megawatt up to a megawatt of cooling, there's no oil separator out there which will do that in a single separator. You're going to need multiple. So I've put a little design tip here, and that is use manufacturer's supply or simulation software and validate oil return velocity. Reach out to the manufacturers, give them the conditions you've got, and get them to verify it. Reach out; they'll be the experts as much as you are. They're the ones who designed it. They know what conditions it's been tested at before it's been manufactured and placed into the field. You use them to your advantage. So, material selection. Hopefully, those present will understand that the pressures inside a refrigeration system can be above atmospheric pressure, and anything above atmospheric pressure poses a risk. Regardless of whether it's a 134A system at 1.1 bar suction or a CO2 system at 130 bar discharge, anything pressurized can be dangerous. But as long as we design for it, we can accommodate it. So with CO2, because people, I'm not going to say it's a new technology, it's been around for a long time, but the components on markets haven't been there until very recently, the last 10, 15 years as such. Making sure you're using the correct stuff is very important. So when you're looking at pipework selections, whereas before you may have been able to use one type of pipework for the entire system, now generally you're going to want to use multiple different types, or you may pick the highest rated one for simplicity, but you'll incur a cost penalty for doing so. So typical pressures we're expected to design to on our low and suction side are between 45 and 90 bar. Yes, huge range there. Generally up to 60 is good and will accommodate 99% of scenarios now. But as pressures are increasing on the intermediate side for efficiency purposes, we may want to protect the evaporators up to the same level. As for our liquid or intermediate side, 60 to 90 bar, depending on how we float the pressure inside our liquid receiver and the quality of liquid we want to send to our evaporators. And then on our discharge and gas cooler, traditionally up to 120 bar, now up to 130. Manufacturers are coming along where ambient temperatures are increasing, and if you're in warmer areas across the globe, you'll get more efficiency or more capacity out of a 130 bar system than 120 bar. That's quite an in-depth topic to go into, so it's one which we tend to leave for course because we could spend hours talking about that and the wonders of the pressure enthalpy chart associated with it. But basically, when you're designing your high side, look to get those high pressure materials. So making sure that they must meet or exceed that maximum allowable working pressure, that PS. But more importantly as well, or just as important, it needs to be compliant with local regulations. So we've got the Pressure Equipment Safety Regulation in the UK, Pressure Equipment Directive in the EU, and ASME in the US. Now, wherever you are in the globe, you'll have your own specific types, which is where it's important as a designer to know exactly what you're dealing with and all your local codes, and being just as up together on the legislative side as the actual fundamentals of thermodynamics side. So I've got a quick selection of pipeworks here where they're appropriate. So K65 is the material you'll tend to find on refrigeration systems, particularly for the suction and liquid sides. They'll work up to 120 bar, providing you specify that type of K65. Stainless steel. See, very, very good across a whole range, very expensive though. Carbon steel, again, it's going to vary on that schedule and the diameter of that pipe, whether it's suitable. Also needs treating when it's implemented because it can corrode. And standard copper, up to 60 bar. So you could theoretically use it on low pressure, low temperature suction pipe work. Would you want to? Would rather put the extra security in for K65. One thing to consider though is even though the pipe thickness will stay the same between K65 and standard copper, the outside diameter remains the same, the inner diameter will change. Because of that thicker wall, you'll have less of an inner diameter on K65, so you'll notice an increased pressure drop, the same length of pipe between K65 and standard copper. So with all this, you need to obviously make a decision as a designer based on local codes and the actual system you're installing. Verify that maximum working pressure and the temperature rating, because as temperature increases, if you're in an industrial scenario where you might encounter very high temperatures, you're going to need to accommodate that as well. Making sure you've got sufficient insulation around the pipework as well. Again, it's very important.
I think that's a big deal, what you just said there. Like as a designer, you want to understand how to make it the most cost effective and safe for your customers. And that can make a big difference on the type of material you'll use. And so designing for success is key, because I love the session where we break it down on what does this whole system cost for a customer. In that section, just okay, these are the types of pipe. This is the price for this amount. I need this many meters or feet, and then that price difference makes a difference when you're quoting a job or you're bidding a job against competitors in your design. So always look at that, and you always have to make sure you're designing it safe, as safe as possible, and look at those codes like Chris said.
Definitely. Depending where you are in the world, you might not have access to some of those materials. K65 may not be available in your market, so you would have to go down the route of stainless steel or carbon steel. Working with what you're given effectively.
Yeah, because I've heard I know quite a few systems that use carbon steel in South America. I've seen pictures and they work and they run. But that's, like you just said, depending on where you're at in the world, you may not have access to that certain material.
So the last one I tend to find which causes issues is poor layout and routing. Whether that is because of an active decision by a designer, you're normally at the mercy of the architects if it's a new building, or working with what you're given if it's an old store. Things change, routes change, room layouts may be built differently from when they were first installed. So looking at how we need to maybe modify pipework or route it to try and minimize any risks of the previous two issues, mainly on oil management, but also minimizing the amount of pipework we have on site as well. The shorter the pipe run, the less pressure drop we incur, the less pipework costs we have. It just makes sense. So why it matters? Well, refrigeration systems are inherently pressure sensitive and velocity dependent, because both of those things, particularly on the suction pipe, will impact the efficiency of our compressors. The longer the route from our evaporator to our compressor, the more of a pressure drop we will get, the more of a temperature penalty we'll incur, and the lower our saturated suction temperature will be. So we want to try and make sure we're routing pipework as sensibly as possible. And what's that include? Well, we don't want to have sharp, short radius bends. We try and use long radius bends. We want to still encourage the pipework to slope downwards, or have to put oil traps in as needs be. What we don't want to do is if you have a building where you're going to have to constantly step down along and step back up around beams. For example, if it's an old building and it's got a low ceiling, try and route it so maybe you go to the outside of the building, run round, back in. Can you move the plant? Can the compressors be moved to another area of the building? All these things which need to be looked at as a strategic design early on in the stage of it, rather than once you've gotten to site as the pipework's being installed there and then. And this has a big cost on the actual cost and efficiency. Every 1 bar pressure drops roughly 2 to 3% efficiency loss, and therefore 2 to 3% more electricity, which all adds up. The longer pipe runs require more installation time, more brazing rod. If you're using stainless steel, you'll need a coated welder in there to do that, and they're not cheap. It's a skilled trade. You need more insulation, you have more thermal losses, you have more superheat. It's a no-brainer. Keep your pipe runs as short as possible.
I think this is where we're working with a lot of people doing these retrofits now, because more and more retrofits are happening. And when you got to look at the bigger picture as the designer. It's not just the pipe work, and it's not just the sizing. When you take control of a project, and that's your project as a designer, you got to look at the bigger picture. And now retrofits for CO2 is happening right now all the time. I'm seeing here in North America, lots of them happening. And as a designer, you got to look at everything. Because if you want to take on a full project, and you may work on a team where you just do the piping, or you may work on a team you just do the sizing. But for us, we want you to be that project man from start to finish, understand that whole project through, because that's where you grow. Understand, because I think this is going to be a bit over the next 5 to 10 years as designers, understanding the retrofit market is going to be huge. Because we know a lot of stores are already coming up to end of life, 25, 30 years out there. They're going to need a transition. And now with all these regulations, with the AIMS Act, and the end users already pushing forward towards CO2 and towards low GWP refrigerants, this, as a designer, understanding how to design for retrofits is going to be super important.
Well, with retrofits, we're at a stage now where both plant and any evaporators all need to be replaced in one go. So it's a big, big cost to the end user. So making sure our systems run, have an efficient life cycle cost, and try and keep capital expenditure as low as possible is very important to make sure you actually sell these systems and install them. Can't make a system if it's the best system in the world, but if it's too expensive to install, you're not going to use it.
Yeah.
So what can we do about the poor layout and routing? Well, let's keep to our best practices. So let's minimize that total pipe length. There's a benefit to us there as well. We reduce our material costs. We reduce our refrigerant charge as well, particularly on liquid lines. Use gentle bends, swept tees, lower pressure drop versus sharp 90-degree elbows. We want to maintain that consistent slope in our horizontal lines for our suction. Between 0.5% and 1%, ideally up to 2% if we can, to encourage it. Want to plan for service access as well. So photo I've got on the right-hand side, a store where halfway after the fact, now a low temperature room then got installed. There's 2 systems, so suddenly you have an extra 2 pipes. Trying to fit that into the same service riser, I'm amazed they could do it, but they did. But now trying to work on that in future, going to be very, very difficult indeed. And avoid U-traps or double bends, and that's specifically not needed for oil return, just one to chuck on at the end there. We don't want to be dropping down pipework and come back up if we can avoid it. Get to a level, keep along that level until we absolutely need to change an elevation. So how can we avoid that? Well, if it's an existing building, go to site, actually look and maybe collaborate with other designers for other services, for mechanical, electrical, ductwork, etc. And if you have access to it, use 3D software, CAD, Revit, or BIM tools out there. Early in the design stage, do clash detection, making sure that your pipes aren't going to be traveling directly through a piece of ductwork, because unfortunately, the pipes will be easy to reroute on the ductwork. Making sure it's all actually coordinated on site before it reaches installation, because the cheapest time to change it is before it's actually installed.
I agree with that so much.
Perfect. And that brings us to the end of today's quick run through of how to try and avoid some issues with CO2 piping. Hopefully it was useful and some people picked some of the stuff up from it. Even if it's just common sense to many of you, hopefully reinforcing it will help you avoid mistakes in future, or pick out mistakes if you see them on site and know then how to fix them.
And I think that's the big thing about there's a lot of different options. And I think one of the things is understanding the code as designer. I know I talk to a lot of designers, some that come through the training programs, and they're like, a lot of my stuff is making sure in each province or each state that the code, we're following the code, because it's different. It could be different. Even here in Canada, across the country, codes are different. Like we have our main national code, but when you get into the provincial code, it can be stricter, and you got to follow your local code. So this is something key for wherever you're at in the world, is that you need to dive into that. And I'm continuing trying to evolve and understand the code in different parts of the world. Where Chris and Nabil, they got it down path for the UK and Europe, but we're looking at codes here in North America, in Australia, around the world, and we're noticing there's a lot of differences. They're not hugely different, but there's differences in the code. And for you as a designer, you need to know what's locally correct for you, or make sure that it's more like a stricter code or a higher level of code if you're going to go for it. So, and I think that's very, very important. And I know a lot of you designers out there are doing that. So keep up the great work, and spend the time to learn it. And it's not always fun. It's not always fun looking this stuff up. It takes time, but doing it right the first time, you don't have to do it a second time. Love it. Okay, we do have an advanced CO2 design course coming up. So if this is something you're interested, ready to take your design career to the next level, as I mentioned in previous sessions, we had over 8 different countries, people from 8 different countries come to take this program, taking their career to the next level. I love this course. I've learned so much in the last 3 times we ran it. And once again, we're already filling this course up. Super excited for it. And Chris, and I'm pumped up. I'm pumped up for this course. So thank you so much, Chris, for taking the time to talk. And the next session is going to be in June, this one here, in a couple of weeks. So definitely get in on that one. We're going to be diving into how to size transcritical high pressure valves, what the do's, the don'ts, what to look for, how to size it for different like summer applications, what you need to look for when it's in the middle of the winter and very low temp ambient, as well as the next one's going to be on flash gas bypass valve sizing, what you need to look for, what you need to do. Another game-changing session. Chris, thank you so much. Look forward to seeing everyone at the next CO2 design session. Thank you.
Take care, everyone.